Yeah, we need to. I'm not gonna do it today just because I want to get through this. Okay, here we go. Here we go. Let's go ahead and put Chromebooks away for just a little bit. You'll get your chance here momentarily, but for now, just look them up. All right, so what we're going to look at today, here's the plan for today. Let's put all distractions away. Phones, etc. Those need to be in your pockets away. So today, we're going to talk about something a little different. Now, what we've done here that's, I think, a pretty good idea is that we've gone through pillars. Thank you. We've introduced kind of the way that we're going to do business for the rest of the year. It's taken a little while, but it's been an important step. We reviewed algebra, which was huge. That's a big deal. We're going to do lots of algebra this year. You've had your first experience of doing the kinds of problems that I really think are the best kind, where you have to take a geometry concept and turn it into an algebra equation and kind of merge the two. That's only going to get easier as the year passes. So now we're just going to apply that way of thinking and that approach to a different topic, lines and angles. And we're going to look kind of specifically at a couple things. We want to be able to identify some new types of relationships between lines and the angles that are formed by those lines. Okay, before we do that though, let's just look at a couple definitions. Not a big deal. Three important definitions of the top one we're pretty familiar with. Parallel lines, we've talked about that a little bit already. You have a pretty good, I'm sure you've talked about it a bunch in school prior to this. So we all have a pretty good idea what parallel lines are, what that means. The technical definition of parallel lines is just two lines that are coplanar. That's really important. What's it mean to be coplanar? Okay, on the same plane. So two lines that are coplanar and do not intersect. Right now, we're going to explore that concept a little more later on in the class, and it's kind of a fun topic to at least talk about. We are restricted a little bit in this class. Really, this class should be called Euclidean geometry or flat geometry. What we do in this class is we study the geometry of a flat surface, or more broadly, a flat space. You might wonder what the heck a flat space would be. Well, a flat space is just a space in which a plane has the properties that we're describing. That may not be the way the universe always works, though. On a really broad scale, we find that the universe is basically flat. So geometry works the way you'd expect it to, but not always. There are places in the universe where it is not flat, where it's spherically warped. So it would be like looking at the surface of a basketball, for example. Geometry works very different on the surface of a sphere. There are other places in the universe where it's hyperbolically warped, which would be like a saddle shape. And with a saddle shape, geometry also works very different. What we find is that wherever the universe is warped spherically, parallel lines do intersect. And wherever the universe is warped hyperbolically, like a saddle, we find that parallel lines actually move apart from each other. And that's true. That really does happen. So we're not going to really deal with that in this class mathematically, but it's kind of nice to understand how that all works. So we'll discuss that sometime. But for now, we're talking about regular Euclidean flat geometry. And for regular Euclidean flat geometry, parallel lines are exactly the way you think they are. Okay, they don't intersect and they lie in the same plane. Skew lines. So what do we call a line? Two lines that do not intersect but are not coplanar. Well, that's a skew line. Okay, that's the other brand of lines that don't intersect. You've got either parallel lines or skew lines. And then the last concept is parallel planes. And we've already talked about this a little bit. Remember, we used our classroom here as an example that helped illustrate what planes are, what their intersections look like. What example did we give of parallel planes in the classroom? I think we gave several, but what's one of them? Say it again? Floor and the ceiling, perfect. The ceiling, if we extend the ceiling infinitely, right, that's a plane. And if we extend the floor infinitely, that's a plane also. And it's a good example of parallel planes because they always stay the same distance apart. They never intersect, right? Okay, so here's a little picture to help illustrate this. We've got this cube, and I want you to come up with some specific lines and planes and things like that. So first one is, don't say it out loud, just see if you can come up with this on your own, and then we'll share some answers. I want you to see if you can come up with a line that is parallel to line AB and contains point D. So a line that's parallel to AB and contains point D. So what do we think? Anybody got an idea? What do you think? What do you think? Line DC, sure, that works, doesn't it? Line DC is perfect because it's a line that lies in the same plane as line AB. The plane is the one that includes the top of the cube, right? The top face. And they're parallel. Yeah, they would never cross if we extended them forever. Perfect. Okay, what about a line that's perpendicular to AB? Now, remind us real quick what it means to be perpendicular. Okay, I'm seeing this kind of thing. What's that mean? They intersect how? At a 90-degree angle. So they intersect at right angles, right? At 90-degree angles. So we want to come up with a line that's perpendicular to AB that also goes through point D. Suggestions? What do you think? Big, like that idea? Line DA? Does that make sense? If this is a cube, then isn't the top a square? Right? And so the edges of that square would have to meet at a right angle, wouldn't they? Right? So that makes sense. Yeah, we could kind of draw that in, and so there's the right angle, right? Make sense? Good, good, good. Okay, what about this one? Skew to AB and contains point D. So we'll make this one orange. Actually, there are a bunch of them. Can somebody give me one example of a line that is skew to AB? What does skew mean again? Okay, they're not coplanar, and they also do not intersect. Okay, good. Trinity, can you give me an example of one that goes through, a line that goes through point D that's not parallel to AB but does not intersect it? Say it again. DH, yeah, good. So line DH right there. Perfect. Right? They don't intersect, but they're not in the same plane. That one works. How about another one? What do you think? Carol, you get another one for me? That contains point D, that's skewed to line AB. Go. Yeah, what do you think? GD? Sure, that works. They also do not intersect, but they're not in the same plane. Shaw, you got another one?
DF maybe?
Yeah, that's a kind of a hard one. Yeah, DF works, doesn't it? D and F, that's the one that goes right through the very center of the cube, right? That works. Good. Okay, I've got another one for you. See if you can, now, another challenge for you before we move on to the last step here. See if you can come up with a line that well, we're going to find some lines that are perpendicular to AB but don't necessarily go through point D. So we want lines that are perpendicular to line AB. See if we can find some creative ones here. What do you think? You got one? Yeah. AF. EF. Is that perpendicular to AB? EF is? There's AB. EF would be on the bottom. Wouldn't that be parallel?
Yeah.
You're thinking parallel. Sean?
CB?
CB works, yeah. There's one. Okay, they're at a right angle. Good. What else? AD works, yeah, we did that one, that's good. What else? AD works. Say it again, what else did I hear? AE works, yeah, that's good. Yeah.
Can you go like
Okay, DB wouldn't work because now think about if I just took the top square. Let me just redraw that top square, right? So say we took the top of this cube off. So that's A, that's B, and that's D, right? Now you can kind of see that if I connect those, here's one line, and there's the other line. What do you think that angle would be right there? Any suggestions? Not 90, it'd be about 45, it'd be exactly 45, wouldn't it? Okay, so that one wouldn't work. Can you find another one? And I'm just gonna say, I don't care what other point it goes through, but let's say it has to go through point A. Perpendicular to line AB and goes through A. We already said AE and AD. Can you think of another one? AH, yeah, that works. How about that one? That's a little harder one to visualize, but do we see that? Right? That makes sense, doesn't it? Would you agree, in fact, that any line that's contained in the front face has to be perpendicular to line AB? Right? Because line AB is coming straight out of the board, isn't it? Does that make sense? And all these lines are parallel to the board. Any line that's contained in that front face, isn't it? So if a line is parallel to the board and the other line is perpendicular to the board coming straight out, they have to meet at a right angle. It's a difficult one to visualize, but it works. It's a good one. It's kind of hard to draw. I guess it'd look kind of like that. Not hard to draw, even at the right angle. But get the idea. Okay, so last one. Planes. We want to name the plane or planes that contain D and appear to be parallel to plane ABE. Well, let's remind ourselves about how we label planes. How many points does it take to define a line? 2. 2 points defines a unique line that's unlike any other line, right? 3 points defines a unique plane. But we have to be careful about the 3 points that we choose. What if we choose, for example, points A and B, and I'm going to choose another point on that edge, and I'm just going to call it X, how about? Are those 3 good points for defining a single plane? Here, I'm shaking her head. How come? You're right. Say it again. Okay, because there's something about those points. Would you agree that points A, B, and X, they lie in the plane of the top, don't they? But they also lie in the plane of the left side, right? Agreed? So those are 3 points that do not define a single plane. They define a bunch. There's something wrong with those 3 points. And you got it. They're on a line. They're collinear, right? 3 collinear points do not define a unique plane. The 3 points have to be non-collinear. They can't be in a line. So if we get rid of point X, and we instead choose points A and B and E, that works, doesn't it? They define a single plane. Now describe for me the one plane that contains points A, B, and E. How would it be on the cube? What plane would that be? Yeah, kind of the left face, right? Does that make sense? Okay, so we want to come up with another plane that's parallel to that. What's the only face of that cube that's parallel to the left face? Yeah, okay, good. It'd be this face, wouldn't it? So one way we could do it, we could say, for example, what did you say it was? CDH. That would work, wouldn't it? What's another way of naming that plane? DCG would also work, right? Any 3 of those 4 points are going to define that plane. Make sense? Okay, and there's only one that's going to work. The rest of them would all intersect the left face. All right. Okay, so moving on here. What we want to talk about today is a couple things. Let's first of all, let's just briefly address this. This is simple, but very important in geometry. Remember that postulates in geometry are statements that are so basic that we don't prove them. We just accept them, right? So Doesn't this make sense? If there is a line, call it line L, and a point P, we'll call it P, that's not on that line, then how many lines could there be through point P that are parallel to line L? Only one, right? There could be only one. If I tweak that red line at all, it's not going to be parallel to line B. Agreed? If I tweak it in the plane by changing its slope, by tilting it a little bit, then wouldn't you agree the red and the blue lines would intersect someplace? Okay? If they don't have the same slope, they're going to intersect. What about if I tweak it by moving it out of the plane of the board? What if I just twist it a little bit so it's coming out of the board maybe? Then it's no longer parallel. Instead, it would be what? What would we call that line? Maybe they don't intersect. What if I just kind of twisted it like that a little bit? It'd be skew then, right? Okay, so there's only one possibility. If I have a line and a point not on the line, there is exactly one other line through that point that's parallel to the original line, right? That's the parallel postulate. Okay, going along with that is the perpendicular postulate. It says almost the same thing. It changes one word. If we have a line and a point not on the line, then there's only one line perpendicular, through the point P, perpendicular to the original line. Any other one is not going to meet at a right angle, or it won't intersect at all. Okay? So we'll come back to those, but I just want to introduce those to you. So the other thing we want to look at then is the situation we get when we have some lines that are cut by what we call a transversal. Transverse in the English language just means across, right? So this is a line that's cutting across some other lines. The definition is, of a transversal is a line that intersects two or more coplanar lines. That's important. So they have to be in the same plane, and it has to intersect them at different points. Okay, so the lines have to be in the same plane. All three lines have to be in the same plane, or it could be even more than three. It has to be at least three. You tell me, I'm going to draw some examples up here, and you tell me if these lines, if it represents a transversal. So say I've got these two green lines that maybe do that. Is the pink line, oops, it's not pink. It's not pink. Is the red line a transversal? Yes or no? What do you think?
Yes.
Yeah, okay. How come? Okay, good, because I have the red line intersects the two green lines in two different places, and they're all in the same plane, right? Okay, another one. Same deal, I've got two green lines. And I've got a red line. Is the red line a transversal? Yes or no? Does it meet the criteria? How many lines does the red line intersect? Two or more, right? It could be even more, but it's two at least, right? So you have to check that off. Does it intersect the two lines in different places? It does. So is it a transversal? Yeah, it is. Right? There are my intersections. Okay, what about the purple line? Okay, what's wrong with the purple line? You're right, it's not. How many lines does it intersect? No, it intersects two. But in only one place, right? Only one point. So that is not a transversal. Okay, good. So if we have that, if we have a situation where we have, let's take two lines that are cut by a transversal. Well, would you agree that every time two lines intersect, how many angles are formed when two lines intersect? Four. Every time, right? I'm going to get four angles. 1, 2, 3, 4, right? So if two lines intersect, if a transversal, how many angles are going to be created? 8. Very good. Okay. So here's the situation we have then. I have two lines cut by a transversal, or intersected by a transversal. the angles that are created have specific relationships that we're gonna work with this chapter. So for example, if two lines are cut by a transversal, like in this case, then the angles that are labeled as 1 and 5 here, the red ones, are what we call corresponding angles. What does it mean to correspond? Like what are things that are like if they correspond to each other, what does that mean? Yeah, they go together, right? Okay, so why is it then? Give me one good explanation for why we'd say that angles 1 and 5 are corresponding angles. Okay, because they're both on the top left relative to the transversal, right? Does that make sense? Another way of thinking about that, what if I took the bottom line and I kind of moved it around so it overlapped perfectly with the top line? What would happen to angle 5? It would become angle 1, wouldn't it? They would be identical, right? They would overlap perfectly. So therefore, they are corresponding angles. Okay, what about these other ones? See if you can come up with the scheme that we use to name these other angles. I gotta make one change because there's one mistake here. That's supposed to be a 6. Okay, what about angles 1 and 8? We call those alternate exterior angles. So those are alternate exterior angles. Angles 3 and 6 we call alternate interior angles. And angles 3 and 5 we call consecutive interior angles. Okay, so based on, on those relationships, what do you think it means to be alternate angles when we have two lines cut by a transversal? What do you think, Nick?
On the opposite side of the transversal.
Okay, good, yeah. So alternate means opposite sides of the transversal, doesn't it? What do you think it means to be consecutive angles? Same side, yeah. Consecutive angles are on the same side of the transversal. Okay, but we said alternate exterior were different than alternate interior. The orange angles are alternate exterior. The green angles are alternate interior. What do you suppose it means to be an exterior angle? Okay, outside of the two lines. Good. Whereas interior angles are between the two lines, right? So then what do you think, give me an example of what you think consecutive exterior angles might look like. Name two angles up here that you think might be consecutive exterior angles. Yeah, 1 and 7 would work, wouldn't they? Consecutive because they're both on the left side of the transversal. Exterior because they're outside of the two lines. Good. Okay. So I want some angles here. Casey, give me name two angles that are corresponding angles. That are corresponding. Yeah. 2 and 6. Good. Okay, Abby, give me two more that are corresponding. 1 and 5. Yep, you betcha. Cassidy, two more. Four and 8. Perfect. That works. Good. Okay, what about alternate exterior? I want alternate exterior angles. Dalton, give me two angles that are alternate exterior. Say it again. 4 and which one? And 8? Oh, okay, those would be corresponding. Right? Those are corresponding. Now, what's it mean? Let's break this down. What does alternate mean? Yeah, so okay, alternate is opposite, right? Exterior means outside. So, Shaw, give me an example.
Could 2 and 7 work?
2 and 7 would work. Good. Caitlin, what's another pair of alternate exterior? 8 and 1. Good. Okay, what about alternate interior? Maria?
4 and 5.
Yep. And another pair? What do you think, Christine? 3 and 6. Okay. What about consecutive interior? Bailey? consecutive interior. So interior, what's the interior part mean? Okay, between the lines, and consecutive, alternate means opposite sides of the transversal, so consecutive means 3 and 5, perfect. Okay, Abigail, what's another pair? Of consecutive interior. 4 and 6, good. And then they don't list this up here. For some reason we never really talk about these, but they work too. Martin, give me a pair of consecutive exterior. 1 and 7, yeah. Okay, another one, Kylie, what's another one? 2 and 8, perfect. We got it. That's it. Okay, that's really section 1 is just about recognizing those relationships. Okay, questions on that? No. All right. Okay, so you may grab a Chromebook. If you need to finish the test, please do so. I'll put the assignment up if you're done with the test.
Basketball court. In a glass house.
Oh, we have an assignment?
Yep, got one coming up here.
So we can't start another test?
You can, if you'd prefer, that's fine. You can do that.
So I why?